Hello dear students, welcome you all. In this lecture, I am going to discuss about the D to A and A to D conversions, right? D to A stands for digital to analog and A to D stands for analog to digital conversions, right? So, here in this lecture, I am going to start this topic because it is a very important topic in digital electronics and D to A and A to D converters, they play a very important role in digital data processing, right? We know very well that all digital machines, whether they are computers, right, laptops, mobile phones, they are using digital signals for processing of the data. I mean, if we are entering the data into the machine, then we know very well that machine understands only the binary language, the language of discrete signals, right? And if in the same way we are taking data out from the machine, then for example, if we are going to drive a speaker, right, then at that moment digital signal is not capable of driving the speaker, right? Then at that time digital signal has to be converted into the corresponding its analog format. But if I'm entering the information into the machine, for example, I'm speaking something and this information has to be stored in the machine, right, in the memory of the machine, then first of all this my voice should be encoded, right, into corresponding digital signal, and then that signal will be processed and stored in the machine, right? So we can say that analog to digital converters are basically encoders, whereas digital to analog signals are decoders, right? They are decoding the digital information and converting it into the corresponding analog format, and encoders, they encode the information to the digital format. You can see here in this pic the entire process of A to D and D to A conversions. As far as A to D conversion is concerned, if we have an analog signal, we know very well analog signals are continuously time varying signals, right? And this signal is applied from this side, then first of all this signal, analog signal, will be passed through an anti-aliasing filter, anti-AAF, anti-aliasing filter. Anti-aliasing filter will remove undesirable frequencies present in that message signal, right? This is the role of this anti-aliasing filter. We have studied it in details when we have discussed about the sampling theorem. Then after that signal will be passed through the sample and hold circuit. I also have explained what is the working and what is the role of sample and hold circuit. Then after it is passed through the quantizer for quantization. Quantization means we are now assigning different voltage levels, discrete voltage levels to the analog information, right? And then finally it is passed to the digital signal processor, and then finally we got a digital output that is in the form of 1 0 1 1 0 1, like that. This is now the corresponding digital output, right, that represent this analog information, whether it is this information is a sound, it is a script, it is any image, right? It can be anything, it is a video, anything can be in the form of analog information, right? Because in nature most of the information that we see, right, that is present in the form of analog signals. So first of all, if we want to process this information by digital processors, right, then we have to convert into the corresponding digital format. Now this is converted into corresponding digital format. Now when as I told you that this information will be processed and stored in the machine, and when we want this information out, for example in a computer, the information is stored in the memory of the computer, and whenever I want to display this information on the screen, then the reverse process has to be done. This information has to be converted into corresponding analog format. So here this is now going to act as the input for this D to A conversion. Then first of all, in the first step we will have a digital signal processor, right? Then after we have D to A, digital to analog converter, right? Then we have sample and hold circuit. Finally we have smoothing filter. The role of the smoothing filter is to remove undesirable frequencies, and then we have corresponding analog output that was used in the beginning, right? So this is the entire process, right, that is followed in all digital data processing machines, right? So in this lecture, right, I'm going to start with this topic. So first of all, we are starting with the digital to analog conversions because they are easier as compared to A to D conversions for understanding. So we will starting with the digital to analog converters, D to A converters, right? Now D to A converters means if we have information in the digital format, for example 1 0 0 1 1 0 like that, then we have to convert into corresponding analog format. So to do so, two type of circuits are used. The first is a variable resistor network, and the second one is a binary ladder. So I'm starting with the variable resistor network. Variable resistor network means we will design a resistive network in which all the resistance will be different, their values will be different. That's why we are saying variable resistor network, right? And that network will do two things. The first thing is each resistor will be given a digital input, right? And that digital bit will be converted into corresponding analog voltage, right? And then after all the outputs of all the resistors will be summed up and we will get the final analog output, right? So variable resistor network, right, it is doing two things. First of all, it is converting each of the bit present in the digital signal into its corresponding analog voltage value. And the second thing it is doing is summing up all the analog voltage converted by the different resistances, right? So first of all, we have to understand that what is the binary equivalent bit. Wait. So binary equivalent bit is the bit assigned, right, to each bit in a digital signal. For example, for better understanding or easy understanding, let's consider that our digital signal contain 3 digits, right, and the signal is 0 1 0 or 1 1 1 like that, right? We know very well that if we have 3-bit positions, then the maximum possibilities, right, maximum levels are 2 raised to power and 8 voltage levels are possible, right? For 3-bit positions we can have 8 different possibilities. I am tabulating all these possibilities. You can see here this is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. All these are 8. 1 2 3 4 5 6 7 8 possibilities are there, right? So in these 8 possibilities we have different combinations of these 3 bits, right? Now this bit position, this is known as LSB, least significant bit, and this bit is known as a most significant bit, right? Now we know very well that the place value of a bit in binary signals, these are binary signals, right? We have learned about the binary number system, octal number system, hexadecimal number system. So in a binary number system, the bit position, the place value of a bit, right? For example, let it is 101, then the place value of this is 2 raised to power 0, this is 2 raised to power 1, this is 2 raised to power 2. So that's why I have written here in accordance with this. These are the place values of these all bits, right? Now, if you look at this table, then the minimum value in these possibilities is this one, right? Let this value is 0 volt, right? Let this is 0 volt, because we know very well when we are converting a digital signal into corresponding analog signal, then that analog signal, if this is the analog signal, suppose, right? If this is the analog signal, then we know very well it must have some minimum value of voltage and some maximum value of voltage. Let's assume that in this case of 3 bits, the minimum value is 0 volt and the maximum value is 7 volt. Don't confuse in it. It is purely a choice, right? We can take any value, even we can take negative. There is no restriction on it. But for better understanding, I am taking minimum value 0 and maximum value 7 volt. Now you can see here in this table, this is 0 volt. Now when we are moving one step means 1 volt, 2 step 2 volt, 3 step 3 volt, 4 step 4 volt, 5 step 5 volt, 6 steps 6 volt, and 7 step 7 volt. So the maximum value in the corresponding analog signal will be 7 volt and minimum value will be 0 volt. Now we want to see, right, what is the place value or bait. I will not call it as place value, I will call it as a bait of LSB, right? Bait of LSB. So bait of LSB is defined as what is its place value, right? Obviously the place value is 2 raised to power 0. So I will assign it a place value 1 upon 2 raised to power 0 into we are taking B. B is the total maximum value of voltage. So here it is what? It is you can see here. So here actually 2 raised to power 0 is wrong. I proceed in the wrong way. So let's erase it. I'm going to assign the bait to LSB, right? Binary equivalent bait to LSB. Now you look at this table first, right? 0 0 0 corresponding 0 volt, right? Then you come across this one, right? This one. Now you can see here 1 is appearing at this LSB position only, but here it is 0 0. It means the 1 at this position is producing 1 volt output, right? You can see here. So it means I can write it as 1 upon 7 into 7 volt, that is 1 volt. Similarly, you can see here, if 1 is appearing at this position, you can see it is equal to 2 volt. So what I can write here now? You can write here that this is 2 times the value of LSB bait, right? Similarly, if you come across this one, right? This one. Now this is the one at MSB, right? Other 2 digits are 0 0. So when 1 is appearing at MSB, I am getting 4 volt. Means it is 4 times the value of LSB bait, right? So you can see here now the bait of LSB. Bait of LSB means if 1 is appearing, bit 1 is appearing at LSB, then I am getting only 1 volt. But if it is appearing at the second LSB, right? Second LSB is this, then it is 2 times. Then at the MSB or third, it is 4 times. Similarly, if I use 4 digits in the binary signals, then it will become 1, 2, 4, 8, right? Then it will become 8 into LSB bait, right? But here I am restricting myself to only 3 bits. So you can see here now, then in general I can write it becomes 1 upon 7 into 7 volt, it becomes 2 upon 7 into 7 volt, it becomes 4 upon 7 into 7 volt, right? So I can write what is the weight of LSB. The weight of LSB is 1 upon 2 raised to power n minus 1 upon 7, right? This is the weight of LSB, right? You can see here. So weight of LSB is 1 upon, here n is the number of bits. If the number of bits are 3, 2 raised to power 3 minus 1 is equal to 1 upon 7. If n is equal to 4, then it is 1 upon 15, because in that case we will have 1 upon 16 minus 1. Similarly, if you have 5, right, then again you will have 1 upon 31. So these are the binary equivalent bits, right? And the corresponding voltages are, you can see, corresponding to LSB 1 volt, corresponding to I am writing here, it is a binary equivalent bit voltage, right? So this is 0, this is 1 volt, this is same thing, right? And that are written here: 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, and 7 volt. Now you can see how this binary equivalent bit voltage is generated. It is generated by keeping in mind that how the 1 at LSB is affecting the output, right? So this is the way of writing down the bits of different bits in LSB. If you have a 4-bit system, right, then the corresponding bits will be 1 upon 15, 2 upon 15, right, then 4 upon 15, and then 8 upon 15. These are the bits of different digits in a 4-bit digital signal. But for 3-bit, I have for LSB it is 1 upon 7, for second LSB 2 upon 7, and for the last LSB, or we call it MSB, it is 4 upon 7. The most important thing is, when you are writing the binary equivalent weight, the sum of the binary equivalent weight of all the bits must be equal to 1. You can see here 4 plus 2 plus 1 7, 7 by 7 1, 8, 4 12, 2 14, plus 1 15, again it is 1. So this is very important. You can be asked in any exam to write down the binary equivalent weight of given bit number of bits. So this is the way of writing the binary equivalent bit, right? Now I'm going to design a variable resistor network that is going to do the actual conversions, and it will do the conversion according to the bit, right? Bit of that bit LSB, then second LSB, and then MSB, right? So now I'm going to draw a resistive divider network, right? Resistive divider network, that is a variable resistor network actually. So I'm doing it for 3 bits, right? 3-bit digital data, right? Digital signal or digital data, right? So for it, you know very well that we need at least 3 resistors, right? 1, 2, and 3. So these are the 3 path for 3 resistors, right? This is the resistance for LSB. This is for LSB bit 2 raised to power 0. This is for second LSB 2 raised to power 1. This is for third or MSB, right? This is the resistance here, resistance here. Let this is R0. This is R0 divided by 2. This is R0 divided by 4. This is the load resistance RL, RL, and it is very large than value of R naught. Here we are getting analog voltage, right? Appearing at this node. This terminal is grounded. Right. Now you can see here a very simple resistive divider network that is used for converting 3-bit digital signal into corresponding analog signal. Now we know very well that this resistor divider is going to do two things. The first, each bit appearing at these different resistances must be converted into the corresponding analog voltage. Then after all these three voltages appearing at these three, they must be summed together to produce the required analog signal. We also know very well that if one appears at this LSB, then the output, if only one appear, I mean if I have 001, then output will be 1 volt. If one appear here, it will be 2 volt. If one appear here, it will be 4 volt. But if I have 111, it means the output will be 7 volt. It means it is going to do these two things. The first thing is convert each bit into the corresponding analog voltage and then add up all these voltages. So to do so, we have taken the different value of the resistances and they are chosen in such a way that this condition is satisfied. So it is R naught, it is half of this. So similarly, if we have 4-bit resistive divider network, the next resistance will become R naught by 8, right, in that way. So now if I want to find out the output, right, voltage appearing here due to the voltage appearing at these three inputs, right. We know very well in the digital signal 0 represent 0 volt and 1 represents 7 volt. This is the voltage level in digital signal. And in analog voltage also, the minimum value will be 0 volt and the maximum will be 7 volt, right. Now, if I want to find out the output voltage that is appearing here because of the different voltages appear, whether it is 0 volt or 1 volt, right? 7 volt here, because in these terminals, two options of the voltage are possible. Either 0 corresponds to 0 volt, 1 corresponds to 7 volt, right. So, if I want to find out the output voltage, B analog, then we have a theorem in electronics that is known as Millman's theorems. Millman's theorem. This theorem is very important in finding out the analog voltage or simply I will say voltage appearing at a node in a resistive circuit, right. And according to this theorem, the net voltage appearing at a node in a resistive network circuit is equal to the net amount of current entering the node divided by the sum of all conductances connected to the node. So if I write it in simple way, the sum of all currents, current are, first current is what? This one. If this voltage is B1 and this resistance is R1, this voltage is B2, this resistance is R2, this voltage is V3, this resistance is R3, then Millman's theorem will states that BA, voltage appearing at this node, equal to the amount of current coming from here, coming from here, coming from here. That is, we are not considering the current going in this direction because RL is considered very high as compared to R naught. So this is behaving like a open switch. When the resistance is very high, then we can say this part of the circuit is behaving like a open switch, right. So then current, all the current is going toward this side, nearly zero current going toward this side, right. So all the currents means B1 upon R1 plus B2 upon R2 plus B3 upon R3 plus so on, divided by sum of all the conductances. Conductance means 1 upon resistance, 1 upon R1 plus 1 upon R2, 1 upon 1 upon R3 plus so on. So this is Millman's theorem. It states that the net voltage appearing at a node in a resistive network is equal to the sum of the currents entering to the node divided by the conductance of all the branches connected to the node, right? So it is possible to solve, find out the voltage in this circuit simply by replacing all the values. So here it is B 1 upon R1 is R0 plus B2 upon R0 divided by 2 plus B3 divided by R0 by 4 divided by 1 upon R0 plus 1 upon it becomes R0 by 2 means 2 upon R0 plus R0 by 4 means 4 upon R0 because we are taking 1 upon R, right? So I got R0 common in all, R0 common in all, right? I got B1 plus 2 B2 plus that is 4 B3, right, divided by 1 plus 2 plus 4. This is the case of 3 bits, right? So I can write it this one 2 raised to power 0 into B1 plus 2 raised to power 1 into B2 plus 2 raised to power 2 into B3. General form I can write plus so on B raised to power n minus 1 2 raised to power n minus 1 divided by 1 plus 2 plus 4. It is 7 2 raised to power n minus 1. So if I have 4 bits, then it will become plus 8 here, then it will become 15. 15 means 2 raised to power n, 4 16 minus 1. So this is the modified form of this Millman's theorem. So I can use this formula for calculating the voltage, analog voltage appearing at this node due to the corresponding digital signal appearing at here. Let's take the case when I have the digital signal, for example 3-bit digital signal, and let it is a 101. 101 means, now you can see here 101 corresponding the voltage will be LSB. It is 2 raised to power 0. It is 2 raised to power 0 into B1 means how much it is? B1. You can see here B1, let it is a 7 volt. 1 means 7 volt plus 2 raised to power 1, it is 0 into B2, not 0 but I mistaken here again, 2 raised to power 1 into B2 is a 0 volt plus next is 2 raised to power 2 into what is, it is 7 volt divided by what is 2 raised to power n minus 1, 7 volt. You can see here, right, what the answer you will get, right? You can simplify it. So you can simplify it, it will become 7 plus 0, I am ignoring it, 2 to the 4, 28, right, divided by 7, right? You will get, it was not volt, it was a number here. I think I have written it 7 volt, again it is wrong, right? In this denominator, this is voltage, right? One thing that I want to tell you that in this particular example that I am taking here, I am taking 0 is equal to 0 volt and 1 is equal to 7 volt. In a numerical problem, you can be given this value depending upon the numerical problem. So there is no need to worry. If they are giving 1 is equal to 5 volt, then here you have to multiply with that. So I got volt, right, 35, that is 5 volt. So 5 volt is the corresponding analog voltage. Now you can see here 101, you can see here it is 5 volt. So this is the exact value that has been predicted here. So this resistive divider network produce the exactly same value, right? When we are taking 0 is equal to 0 volt, and 1 is equal to 7 volt, right? So this is the way. If we are taking 4-bit signal, then the things will change according to that, right? And this resistive divider network will contain this additional resistor here, and then it will got connected to this. It will become R0 by 8, and this will become 2 raised to power 3, right? So this is the way of finding the value of the analog voltage or analog signal corresponding to digital input by using resistive divider network, right? I am taking a numerical problem based on this. Let me take it. The question is for a 5-bit resistive divider circuit or divider network, find out the following. Find out the following. Number 1, it is the weight assigned to each bit. First thing. Second thing is change in voltage, output voltage. Due to each bit. And the third thing is you have been asked to find out the output voltage due to the signal input, that is 10101. This is the input signal, and you have to find out the corresponding analog voltage. It is given 0 is equal to 0 volt and 1 is equal to 10 volt. Right. Now, first of all, you have to find out the binary equivalent bit. Right. Here it is plus 7 volt. Even it can be negative. You have to remember it in the mind. If it is negative, then the things will get changed, particularly when we apply the Millman's theorem. So first of all, bit, binary equivalent weight. We know very well it is equal to 1 upon 2 raised to power n minus 1. So 5. So it will become 2 raised to power 5 minus 1. So 1 upon 31. Right. So 1 upon 31 is the bit of LSB. Right. Similarly, for the second LSB, it is how much? It is 2 times the bit of first, 1 upon 31. For the next LSB, it will be 4 upon 31. For the next, it is 8 upon 31, and for the next, it is 16 upon 31. These are the binary equivalent bit of all 5 bits. This is for LSB, right? And this is for MSB, right? 1, 2, 3, 4, and 5. The second thing that was asked was the change in voltage due to all bits. So for change in voltage, due to LSB, it is equal to how much? Because 1 is equal to 10 volts. So 10 multiplied by 1 upon 31, I can say it is 10 upon 31 volt. Similarly, second LSB, it will be bit is 2 upon 31, means 20 upon 31. Similarly, for the third, it will become 4, right? 4 means 40 upon 31. Similarly, fourth, 80 upon 31. And similarly, fifth, or we can say it is MSB, it will become 160 upon 31. This is the binary equivalent weight of all the 5 bits, not binary equivalent weight, but change in voltage due to all these 5 bits. Now the next thing is they have asked the output analog voltage corresponding to the signal, that is output B analog voltage due to signal 10101, right? We know what is Millman's theorem, right? 2 raised to power 0 B1 plus 2 raised to power 1 B2 plus 2 raised to power 2 B3, or even I can write, yeah, it is comfortable, then plus 2 raised to power 3 B4, then 2 raised to power 4 B5 divided by 2 raised to power n minus 1. So you look at this, n is 5, so denominator we will have 31, right? 2 raised to power 0 into 1. 1 stands for 0 is equal to 0 volt, 1 is equal to 10 volt. So 1 is here, so 2 raised to power 0, so it is 10 plus, then next term is 0, this is 0. You can see here, this is 0 and this is also 0, right? So we have 2 raised to power 2, 4 into B3, 10, right? This one. Then again this is 0, then we have 2 raised to power 4 plus 16, right, into 10. So it becomes, if you take 10 common, 1 plus 4 plus 16 divided by 31, right? So it becomes, after simplification, you will get 210 divided by 31, E analog. When you will simplify it, you will get plus 6.77 volt. So this is the corresponding voltage. Such type of questions are usually asked in the exams, even in the competitive exams. But you can see here, it is very simple, but you have to know the Millman's theorem, right? Then applying Millman's theorem, I can find out the output analog voltage corresponding to the given digital signal. So this is all about the first kind of a D2A converter, that is variable resistor network, right? In the next lecture I will talk about the binary ladder, right? So thank you very much.